One day a reindeer is going to come crashing through your bedroom window because you didn't solve the advent of code problem. Welcome back, everyone. It's day 3. We've got 4 stars. We're about to get 2 more if I play my cards right. As always, we are going to be doing the problem from scratch together using Ellie. Hello. We're going to write code on the left. We're going to see it change on the right. Yeah, we're going to just kind of walk through the problem one step at a time. And I haven't seen what it is yet, so hopefully it's not too hard. Let's take a look. Okay, day 3, mull it over. Our computers are having issues, so I have no idea if we have any chief historians in stock. You're welcome to check the warehouse, though, says the mildly flustered shopkeeper at the North Pole Toboggan Rental Shop. It looks like it's going to be an acronym, but it isn't. The historians head out to take a look. The shopkeeper turns to you. Any chance you can see why our computers are having issues again? The computer appears to be trying to run a program, but its memory, your puzzle input, is corrupted. All the instructions have been jumbled up. It seems like the goal of the program is just to multiply some numbers. It does that with instructions like mul x comma y, where x and y are each 1 to 3 digit numbers. For instance, mul 4546 multiplies 45 by 46 to get the result of 2024. Similarly, mul 1234 would simply multiply 123 by 4. However, because the program's memory has been corrupted, there are also many invalid characters that should be ignored, even if they look like part of a mul instruction. Sequences like mul 4 star, mul 6 comma 9 exclamation point, and all this kind of jumbled input should do nothing. For example, consider the following sections of corrupted memory. So we've got all this stuff. Only the 4 highlighted sections are real mul instructions. Adding up all of the results of each instruction produces 161, because this is valid. 2 times 4, 5 times 5, 11, 8, and 8, 5. Interesting. Scan the corrupted memory for uncorrupted mul instructions. What do you get if you add up all of the results of the multiplications? So let's see if we can do this. This is going to be an interesting moment in the video where I either decide if I'm just going to do normal string stuff and just, like work my way through this left to right, or if I use the Elm parser library. I feel like I'm going to do it the string way, and then I'm going to regret it because I should have used the parser. But parser loops are enough reason for me not to do parsers. Anyway, there's a really nice parsing package to solve this kind of problem. But I think what we can do is we can take our string, we can break it into characters, and then we can kind of work our way left to right and see if we can parse the appropriate thing. I really want to use a parser, but I'm afraid I'm going to waste hours of my life if I do that. Let's use a parser. We're gonna do it the fun way. Elm parser. It's not advent code if we're not learning something. There is a package called Elm parser. The past 2 days we have been using the core library, but I'm gonna see if I can wrap my head around how to make a parser that will do this for us. So I'm just gonna add this in Ellie. You can add packages. So we're adding a parser package here. And I'm going to import the parser module, and I'm going to expose some types and some operators that are going to be useful to us, hopefully. So how parsers work is you can take a string, you do parser.run, and then you give it a parser. And what a parser is it's something that returns like some type of data structure. So let me comment this out. What we want is basically a list of expressions to come back. So I'm going to call that expression. There's going to be a multiply expression that's going to take in 2 integers. If it's valid, it's going to look like this. And for everything else, we're just going to ignore it and treat it like garbage. Treat like garbage sounds really rough, but what we're going to try to do is we're going to try to make a parser for expressions. I'm going to just call it expression instead of XPR because I don't think we're going to type it that much. It might as well be a readable word so you don't have to have the cute 4-letter abbreviation. But the idea with a parser is that you kind of start with like the data structure that you're trying to build. So like mul is like a constructor. It's going to take in 2 integers and it's going to return an expression. And the idea is you want to use a combination of this drop operator and this keep operator to say like, I expect, you know, mul parenthesis, and then I expect an integer, and I want to find a comma, and then I want the other integer, and then I need a closing parenthesis. But this is the high-level idea for the parser. I think this is valid. And so what you can do is you can run that parser, and you're either going to get an error. So for example, the first letter here is an X, which it didn't expect. So let me just use a different string here. What we can do is we can say mul to 4. So this parser should succeed with this input because we're specifically expecting mul to start it. And this is an Elm library that makes it really easy to basically say like, look for mul parenthesis, and then this period says like, but drop it, ignore it. Then look for an integer, and then the equal says keep it. So basically pass it into this mul expression. And to give you a sense of what mul is a custom type variant. So mul is kind of like you can think of it like a function that takes in 2 integers and returns an expression. So what we're doing is we're basically using these equal signs to collect those integers as we find them in our string. And then we're passing the first integer and then the second integer in as arguments. And then the result is we get this expression. So if I change this to 20, I get 20 in my output. If I change this to 14, I get 14. And all of a sudden, we have like valid instructions. So this is a kind of the mul parser. This only works on a single, like, it looks for like a specific one of these. So for example, this would fail, this would succeed. And so what we need our parser to do is we need it to basically chomp until it finds an M. And then as soon as it finds an M, run that mul parser. And if the mul parser works, great. If not, we're just going to keep chomping. So I think what we need is we're going to need a loop. So let me get rid of this. Parser. So for this loop, I want a list of expressions. And I'm going to use the parser.loop function. And I always look this one up. I always forget exactly what's available. But the idea with a loop is that you kind of have these 2 states that you return at the end to let the parser know if you're going to keep going or if you're done. So what we can do is we can kind of keep chomping until we run out of the like text to chomp, in which case we'll just kind of return from the loop. So we're going to kind of do something like this. We're going to have like loop, parser.loop. We'll start by saying we don't have any expressions, and then we're going to make a little helper function that's going to look something like this. So I'm just going to kind of copy this. For reference, we're going to put this in a comment so I can just quickly see it. And we're going to do something really similar. We're going to say parser loop, and then we're going to say this is going to be the parser helper. And the idea with the parser helper is it's going to kind of look like this. So rather than having a list of statements, we're going to have a list of these expressions. And then I'm just going to call this step. Each step of the expression is going to be a parser step that has these kind of 2 return types, the state and then kind of the final return value. So state is what we're going to have each time we loop, and then A is going to be like what we have at the end. So I think step is going to be a parser.step where the final, like the state we're keeping track of is just a list of expressions, and the final thing we return also happens to be a list of expressions. If we were making a more advanced parser, these two types might be different. But for right now, it just looks like silly repetition. Expressions. So when this gets called, we're going to pass in the existing expressions. So when it first runs, it's going to be empty. And then the idea is we're going to say parser.oneOf, and we're either going to say we're done, and here's the value we want to return, or we're going to say keep looping. So let's try that out. Parser.oneOf, and I'm going to say I usually mess this up. So parser.succeed. I think what I want to do is I want to try the mul parser. This is the part that I was worried about for the video. How do I do this? Parser.chomp until m. Let's see what chomp until does. End or chomp until end or string. End m. So we're going to try to run the parser. If that fails, we are going to this is going to keep looping parser.loop. Sorry, parser.loop. And we're going to say expression, put it in the front of the existing expressions. I think that's right. And then we're going to chomp till the end or m. And if we can't do that, how does that one work? We chomp until m. I think I'm doing something wrong here, but the idea is that either I get an expression and the mul parser works, or I just succeed and I say I'm done. And I'm going to reverse my expressions. I've been appending to the front, so I kind of want to like append to the... I don't know if this is going to even compile. That's that. This I'm missing. And then, oops. Yeah, and then I think that's the idea. Succeed, and then I'm going to map that through done. I think that's the same as... Wow, that seemed to work without crashing. So does that just work on the input string? That's what I'm worried about. I'm going to save right here. We're going to copy this in case I crash the computer. That's what I'm worried about. So it's really easy with loop for me to get into an infinite loop situation. So what I want to do is I want to take this, close this. It's really easy for it to just keep looping forever. And I think the chomp until never fails. Shoot. Exit page. Cool. Oh, it's going to keep doing that. Man. So this is why I was afraid to use parser.loop, because when I do this wrong in Ellie, bad things happen to me. All right, I'm going to exit. It's going to say there was a crash. Do you want to recover? Where's the recovery? Dang it. There's a way in Ellie for you to basically say Ellie app, and then it should tell me that it recovered from a crash, but I think that's broken right now. Shoot. Okay, I'm gonna figure out how to do this. I think the way I'm gonna do this is incredibly hacky. I'm gonna save this. I've got the thing on my clipboard. I'm gonna share this link. This is gonna put it in an iframe. I'm gonna use this embed URL. What? Not the whole thing. I'm gonna put the ID from this here, and hopefully it won't run it. And then I get my code back and I come back. Okay, that was some next level stuff. You guys don't need to know how to do that. I'm just impressed I saved this video because we're doing it live. I think the issue is, so this is failing for sure, but then this is what needs to, this loop is happening forever. So I think if I got rid of this, if I commented this out, we wouldn't have the infinite loop anymore, but our problem would be wrong. Oops, and I have to reinstall parser. Okay, so perfect. So this fails because it hits the X, and it's like, that's no good. So what I'm gonna do is I'm going to I'm gonna try this. I don't think this is the right way to do it. Oops. But what I can try is parser succeed identity. Let's see if this breaks it. Jump it. Okay, expected mul. This is the debugging parsers is like a skill I need to work on. So I think like eating one character at a time. Here's what I'll do. I will chomp if. Shoot. I think chomp if will fail if I don't. So there's chomp if, chomp until you see a certain string. Chomp if will fail. Chomp while can lead to tricky situations. So like there's basically I want to get rid of stuff. I want to keep chomping as long as there's nothing there. So I think I'm just going to do a single chomp if, and we're just going to have a really crazy parser. So chomp if char true. So I'm going to try to run the parser. If that fails, I will chomp. If I'm able to chomp, I'll continue. If not, I'll be done. I think this is what I want. Yeah, this looks good. So this will let me move through. This will allow me to keep looping. This will fail if I hit the end of the string. I think this will work. I'm going to copy this time, and we're going to try this. Expecting close parenthesis, parser, x mul, chomp if true, this be done? Sure. Column 48. So I just want to see what that is. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why did I count like that? X 5, 5. Where is the 48th string here? So this should succeed and give me an empty list. Okay, that makes sense, because what it's doing is it gets to X, it tries to run the parser, that fails, and so then it moves on. What I'm trying to figure out is why this isn't failing. Chomp if parser succeed, does that, it does this. So let me just all right, so mul 2, 3 should work. This should work. And I'm going to say does mul 3, 2 right after also work. Okay, so these seem to work. If I put an X in the middle, it still works. If I put an X at the end, that still works. What I'm worried about is like if the mul, if it's chomping, I don't know why this wouldn't work. Succeed, keep looping. This fails, you chomp. This fails, you chomp. Because like this is the error that I'm getting. Oh, I think what's happening is this is starting to chomp. It's failing, but it's not falling back. So I think this has to always succeed. I don't think this is any different. But maybe this is important. Try this out. Identity. This is expecting a closed thing, but this shouldn't be upset. This should just move on to the next branch. I think the problem is that the failure is happening in here. And so if the failure is happening in here, it's like, it's moving on. So I'm trying to figure out how to make this more chill. I think it's because it's like, it's consumed enough for it to fail. That's annoying. All right, I have to figure out how to deal with failures. Fail. Problem. So yeah, it's this whole one of thing. I'm afraid I'm going to use backtrackable, even though I don't think that's the right way to go. I think backtrackable is going to allow me to fix this bug, but I don't think it's the right, like it's not the most efficient way to make a parser. Parser backtrackable. Okay, that's what I need to do. All right, so backtrackable, as it starts chomping the parser, I know enough about parsers to be dangerous. Basically what was happening was it would get to this spot, it would fail, and then it wouldn't be able to like kind of like go back to where it was. It was just like it was like down this branch and then it failed, so the whole thing failed, which is something that was really confusing to me as someone who's used to JSON decoding, where one of always kind of recovers. So it's not a one-to-one JSON like decoder metaphor, but all of that crazy ununderstandable code, all the confusion, it led to something good happening, which is that I think this is what we should expect. 2, 4, 5, 5, 11, 8, and 8, 5. 2, 4, 5, 5, 11, 8, 8, 5. I think that's exactly it. So all we're going to do is, now that we have these expressions, we're just going to, I'm going to do result that with default. So if the thing fails, we're just going to say there's no expressions. This will get rid of the OK in the front. And then what I'm going to do is I'm going to kind of like add these up. So I'm going to say list.map. I'm just going to make a function called evaluate. And what evaluate's going to do is it's going to take in an expression, and it's going to return an integer. For now, every expression is something that can become an integer. But if this thing's going to make us write a computer, then we're going to have a bad time. Cool. So that is the evaluation of all these things. So 8, 25, 88, 40. We're getting a little bit closer here. 8, 25, 88, 40. And then when we add all those up with my favorite function, the function that never fails me, list.sum, then we'll be all set. Let me add that in. Cool, 161. And I just realized that the screen here is totally white and bright and blinding. It's my bad. I have CSS to fix that. Let me grab that template for you. This is a part of my base template, is to make it a little bit nicer for streaming. So I'm just going to copy this HTML and CSS and put that in here, so you don't need to be looking at this glaring white background. But 161 is the answer that they got, so I think we're in good shape. What I'm going to do is I'm also going to take this name, and I'm going to go in here, and I'm going to say day 3, part 1. Let's see if this works. I'm going to save this, copy it. We're going to put that in for part 1. These links will be in the description. That's why I'm saving them now. And then, yeah, let's see if I can do it with my puzzle input. A lot of text in there. All right, so I get a crazy big number, 183380722. And that's right, that's the first gold star. So that's good news. Great, our parser seems to be working. I'm hoping that by making this parser that I set myself up for success for this part 2, but we'll see. I'm hoping they're like, what about divide, you know, something like that. Oh, they have a don't. All right, they have a don't and a do. All right, part 2. As you scan through the corrupted memory, you notice that some of the conditional statements are also still intact. If you handle some of the uncorrupted conditional statements in the program, you might be able to get an even more accurate result. There are 2 new instructions you'll need to handle. The do instruction enables future mul instructions. The don't instruction disables future mul instructions. Only the most recent do or don't instructions applies. At the beginning of the program, mul instructions are enabled. So this is actually perfect. As we evaluate, we're going to work left to right, and we're going to kind of use do and don't to flip the state of the program. So here is the same, I think this is the same example they had before. Yeah, they have the do and the do not, that kind of stuff. So let me just make sure that this is verbatim what I copy pasted. Oh, okay, it looks like it is different. So don't. So when I do this, 161, we're back to normal. Okay, cool. I'm just going to comment this out here. I'm also going to rename this to part 2. What am I doing? Part 2. Saving that before I forget. Cool. So this is our existing parser. What they are adding is they're adding a do and a don't. And it looks like, I'm going to close this. I'm going to move this over here. It looks like we want to look for do and we want to look for don't. And we're going to add that to our expressions, basically. So we're going to add do. That's what I love about custom types. This is a very good time. And evaluate's going to behave a little differently. So instead of just having an integer, This is going to be kind of like the sum or whatever. There's going to be like a kind of a different output here. So I'm not sure exactly how this is going to work yet. I'm just going to comment this out. But the high level idea, the thing I want to focus on, is that we want to basically make a do parser and a don't parser. So we could make it its own expression if we want, or we could say parser.token do. If we get that, then we want to succeed and kind of add that to the expression. I think this can all be in a one of. So these are all expressions in which we want to keep looping if we run into one of these. So I think that's right. So parser token do, and we're going to say if we hit one of these, we're going to succeed, and we're going to give it the do. And if we get a don't, is it don't with an apostrophe? It is. It's a don't with an apostrophe. We're going to say don't. And then for all of those, we are going to basically add it to the front of the expressions, and we're going to keep looping. So if we successfully parse one, we'll move forward in that way. So parser succeed. I don't think that I'm using that right. We're going to do that. Cool. Yeah, some of these operators are crazy, so it might be a little tricky to look at. But if I compile this, what you'll see is with very little code, we just like added like succeed with do when you see this, succeed with don't when you see this. With very little code, we were able to capture the mall, capture the don't, capture the mall, capture the what is the next mall? But you'll see that like this is what the puzzle calls out. So mall, don't. Yeah, okay, so it's not highlighting these because it's ignoring it. We're parsing them, we're just gonna ignore them when we evaluate. So the idea here is we're gonna keep doing this. So we have our list of expressions, and then when we evaluate, it's gonna behave a little bit differently. So evaluate, this time around, is gonna use a list fold L, and we are gonna have kind of like a running total that we're gonna keep track of. So we're gonna say the total is 0 initially, and enabled is true, just like the puzzle said. In the very beginning, the mul instructions are enabled. So we're gonna work through one instruction at a time using this fold, and the fold L is gonna work left, that's what the L stands for, left to right, and each time we get an instruction, we're gonna modify kind of the state of our program. So I'm gonna call this initial state. We're gonna make a type alias here called state that has the total and has the total, and then it has enabled, which is a Boolean. So initial state is going to be like this. In the very beginning, when our program first starts executing, we're going to have that initial state. And then what evaluate is going to do is, rather than returning question mark, question mark, question mark, it's going to take in the existing state and return the new state. So this is really similar to the Elm architecture, but it's going to be a little bit different. So the state is going to be that the total equals whatever the state's total already is plus this new a times b. So that's what happens when we hit a mul instruction. When we hit a do, we're going to want to set enable to true. And we hit a don't, we're going to want to set enable to false. And an important thing is that in this program, I need to ask if we're enabled, then we're going to do this. Otherwise, we're going to leave the state alone. Multiply is going to be ignored. But notice that like do and don't aren't going to be ignored. So this is, I think, the way to go. Let's see what happens here. So if I evaluate, what it's going to do is it's going to take this, it's going to do 8, it's going to hit the don't, it's going to ignore these, and then it's going to hit the 40. So hopefully what we see is total is 48. Perfect. and then we end on enabled, which is exactly what we want. And we can use the record field accessor here to just grab that total at the end. And so 48 is what we get. So hopefully that proves that the Elm parser approach was the right way to go, because that was so easy to add. We added the evaluate. Let's save that. I think I already named it part 2. Copy this to the clipboard. I'm getting pretty cocky here, thinking that my code's gonna work with my practice input. But I have faith. I have faith. So here I'm gonna paste. I'm gonna run it, and I get a very big number. What is that? It's 82 million and something. And we did it. That's 2 stars, folks. Sorry about being confused about parsers for the first, I don't know, 20 minutes, maybe longer of your life there. Not of your life, you're not a newborn baby. The first 20 minutes of the video, that was a bit of a tour. That's why I really looked at myself, you know, I really looked death in the face when I was like, am I gonna do this as an Elm parser video? This wasn't a great intro to Elm parsers, but hopefully you learned a little something along the way. And hopefully in the next video, we will not be using parsers and your life will be easier. I'll see you there. Goodbye.